Welcome, everybody. I'd like to invite you to our Sustainability Lecture Series, Solving All Problems with New Ideas, which is a 6-part series of sustainable design solutions for the built environment. The series is presented by the Green Building Committee, which is a subcommittee of the Environmental Performance Advisory Committee. A lot happens on the campus with committees, obviously. The Green Building Committee has teamed with facilities planning, campus planning, landscape architecture and regional planning, architecture and design, the Historic Preservation Initiative of the College of Humanities and Fine Arts, and environmental conservation, to present this series with the goal of expanding our collective knowledge and commitment to sustainability on campus. I'd like to acknowledge our green building researchers, Catherine McCusker, Katrina Spade, Bill Stanton, and Lawson Wilson. Please stand up. These students have put in enormous energy and enthusiasm into this. And I'd also like to thank the environment for hosting this lecture and working with us to promote it throughout campus. Absolutely, they do fabulous work on system-wide sustainability. Please join us in 3 weeks for a talk by Louis Capozzi, who is facilities engineer at the Genzyme Center. The talk is entitled Life in a Platinum Green Building. His lecture is on October 18th at 4 o'clock in this room, and we hope to see you all then. I'd also like to do a few nuts and bolts. Please silence your cell phones. Today's lecture is eligible for continuing education credits for both the AIA and the USGBC through For those of you who are looking for GBCI credit, there's actually a handout to help you document the lecture in the back of the room. On the handout is a website where you can also download the presentation slides in a week or two when we get it all up. umass.edu/FP for facilities planning, FCP publications. On your seat is a short survey. Fill out question 1, and I'll wait for about 60 seconds while you all do that. Could somebody touch the lights up, please, so that everybody could fill out question 1? We're really looking for feedback and from all of you. Survey, please fill out question 1.
You're fine.
If you'd like to find out about future events sponsored by the Green Building Committee, please leave your email address on the survey. After the lecture, complete the survey and return it to one of the students out. This lecture will be made available through the Facilities Planning web. I also have the privilege of introducing Fiona Cousins. My name is Mila Pavlova, and I'm a senior facilities planning. I have the privilege to be working on the campus master plan, which went through a series of open forums and is in the process of developing a draft master plan framework for our next, 10 to 50 years opportunity of building and creating campus. Our committee has been engaged in ongoing both capital plan investments and a significant operating budget to support the many functions and mission, the main mission of the university. And in the last 5 years, our capital plan is from 2005 to 2009 represents about $802 million of capital expenditures alone. Capital expenditures are actually funds that are put to, such as property and buildings and mechanical equipment and systems that support many, many functions, from offices and classrooms to research and other outreach activities that the campus does daily. In a sense, money equals buildings, and in a way that is much more real, buildings also means energy. Fiona Cousins, who is principal with Arab in New York, will be talking about energy buildings. And I'd just like you to keep this in mind in terms of capacity in our campus, both on the part of campus planners, physical plant managers, facilities planners, students who will join us in the workforce within a few years and will become the future environment. So hopefully will be applied in such a way that our funds, our tax dollars, the best way so that we can save energy and get the most functionality out of it. From the University of Cambridge, with degree in interdisciplinary design for the built environment, she joined Arab's London office. Over the years, she has worked at Arab's and is currently a principal with the New York office. She also served for 2 years as the chair of the New York chapter of the U.S. Green Building Council, and the staff grew from 1 person to 8 people. Fiona has understood the thermal performance of buildings. This enthusiasm for low energy design and technical performance has driven her work throughout her career. Analysis of thermal behavior and continuing to lead with solutions where each discipline plays. She has had the opportunity to apply this approach in her recent work, laboratory and gallery projects director. The parallel thread performance buildings have inspired a practice that specializes in translating ideas into practical programs of action. On the New York Power Authority Sustainability Plan, on the Middlebury College, on East River Waterfront in New York, Central Library, Fulton Street Transit Center, NYSERDA Analysis, that's the New York State Redevelopment Authority, and Lincoln Center Campus Master Plan. Today's lecture is on energy in buildings. Welcome, Fiona Cousins.
So I thought that I would start by talking a little bit about me, and then talking a little bit about energy in buildings, and then talking a little bit about 3 things that you should know. So the first building that I wanted to talk about, and this is really me trying to prove that I sort of know what I'm talking about, is the Joint Research Centre in Italy. It's a project that I worked on, and it's a long time ago. And the thing that we were challenged with at the Joint Research Council was that they wanted to renovate some of their buildings which they knew were performing badly from an energy standpoint, and they wanted to make sure that the paybacks on those were such that they could fund the entire renovation of the building. And they were quite generous, more generous than most people usually are, because they said that if it can pay back in 20 years, you can do it. So this is the cafeteria, a building that I actually got food poisoning in, but otherwise has food fond memories. And it was originally a single glazed glass box, and we worked with an architect called Mario Cucinella, and we did all of the things that we could do to save energy. And the things that we decided that we would do were to shade the roof, so it was actually less expensive than lating it, to add a solar hot water system, big kitchen, so it had a big solar hot water, big for the dishwashers, and we also wanted to make sure that it had shading on the outside of the building, so you see that we've turned some of those all glass to wooden panels. So this was 1992. In 1992, people really didn't know how to do energy modeling. They hadn't really tried it. They didn't know how it would work. The programs were terrible. So we did most of this through a kind of analysis that looked at all of the hours of the year and came up with some cost numbers. And it was a competition, so it was actually quite difficult to do, but it did get built. And it's one of the projects that was very early on in my career. I think I've been working for about 2 years. That sort of started me off on this path of thinking about low energy. So the second project that I wanted to talk about was this one. This also has an approach to low energy within it, although it's not quite so obvious. New Caledonia, which is where this project is, it's a Renzo Piano project, which I'm sure that the architects amongst you have seen. It's the middle of nowhere in the Pacific Ocean, in fact. And they don't really have a mature HVAC industry on the island, so everything that we wanted to do had to be it basically had to work if the air conditioning broke, because if the air conditioning broke, it might be 6 weeks before they could actually get a replacement part. So they wanted air conditioning because it's actually very hot and very humid, but they wanted to make it if it wasn't there. So this whole piece, how can we make the buildings work the very best that they can in the climate that they're in, air conditioning, but if the air conditioning, then the buildings can still continue, which is actually a different way of looking at a low energy. How do I make it so it almost works without this? That I worked on, this was the first project that I worked on when I came to the US in about 1996. And the goal here was to try to reduce the peak power demand and also to reduce the energy use over the course of the year. And I'll talk a little bit more about energy and power in a minute. But when I arrived, the project had actually largely been designed, and we had rather bravely said that running fans overnight to pre-cool the slabs in the underfloor system would save more energy than it used and reduce the peak power demand by reducing the peak cooling capacity. And further, we had said that we would manage to reduce the peak cooling capacity by enough that PG&E, the local utility, would aid. So my job when I first arrived in the office proved that all of that was actually true. And luckily for me, it was. We showed about a 20% reduction in peak power for the chillers, which is a small reduction on the building load, but a significant one. And we also showed a 10% energy reduction even after landing the fans. So we did get the rebate from PG&E, and everybody went away happy. This building, I think many of you will have seen, but it was the first building in the US that got the label, the capital G, a McDonald in association with Gensler, and based around courtyards only to the ability to be naturally ventilated, an underfloor air system, lots and lots of daylight. Many things that are actually quite low technology, really the idea of solving new problems, no old problems with new ideas. This is really about solving old problems with old ideas, but they seemed very innovative at the time. Another project which was pretty influential in the way that my thinking developed over time was this project. It's the Nursing and Biomedical Sciences building in UT Houston. And this project was one where the owner said that they wanted to design the building according to natural step principles. Natural step principles basically say you can't dig anything out of the ground and you can't emit anything at all. So from a sustainability standpoint, it actually makes everything very challenging. So we worked on the schematic design of this project for about 3 years. Those of you who've been in industry will know that that is an incredibly long time. And we worked on it with an architect called Packhow out of Vancouver. We didn't actually build the project. I think that after 3 years, the client was fed up at the sight of us, and it was built by BNIM and Lake Flato as the architect. But many of the ideas that we had at the beginning of the project were maintained into the project itself. So the things that it has that were unusual for the time and interesting, it has rainwater storage and collection, it has PV arrays on the roof, or at least the space for putting them in, it has underfloor air, it has, this is very, very unusual, it has a different facade design for every face, so that the north side looks different from the south side, looks different from the east and the west, so that they all respond to the climate. It was also unusual in the level of analysis that we did in early stages. We did a huge amount of energy modelling right at the beginning, which is a stage of the project that we wouldn't normally do, just to see what the overall effect of things like the HVAC system changes and additional insulation and the facade changes would actually have on the outcomes in the end. It was unfortunately still only 1997, so energy modelling was still a difficult and expensive thing to do, and we didn't quite nail all of the answers that perhaps we would have been able to nail now. And the last project that I'm going to talk about is the Princeton University Chemistry project. This project we started work on in 2005 and it was completed in 2010. And you wouldn't really expect that a lab would be a poster child for energy efficiency. But this building has about 400 lab hoods. And the issue with a lab hood is that it exhausts air. And once the air has been exhausted, it can't be reused because it's full of all of the nasty things that you were trying to take away in the first place. So the building systems have to provide significant fresh air makeup at temperatures that are comfortable for the researchers. And it's that temperature difference, whether it's from hot to moderately temperatured or cold to moderately temperatured, that uses a great deal of the energy in a lab. So the project took a number of steps to reducing the energy use. We used high efficiency fume hoods that use less air to achieve the same results. We have variable volume hoods that reduce the airflow required when the sashes are closed. We have automatic sash closing devices so we can make sure that the sashes are actually closed. We used a minimum fresh air system in the office space and then recycled that air through the atrium and then through the lab. And that helped control the amount of air that needed to be brought to temperature. We also have PV on the roof, rainwater storage, heat recovery, chilled beams. There's a whole panoply of stuff that we did that falls into the category of the things that you need to do to save energy. There are a couple of things that I think we could draw as conclusions from all of these projects. There's never just one solution. Energy saving needs a little bit of everything. And it needs all of the disciplines involved in the projects to prioritize it. So if you have a project, or I have a project at the moment where we want to achieve full transparency and we want to achieve LEED Platinum, and it's actually pretty close to impossible to do both of those things at once. So the priorities of the client and the architect and the engineer actually in themselves need to be prioritized. It's all very well to say you have 6 different priorities. Sometimes those priorities are in conflict, and that prioritizing the priorities is actually one of the biggest decision-making problems that we run into, especially in energy saving. The second thing is that good results really come as a result of a collaboration rather than from one individual discipline. So for the hoods on this one, they needed us as the engineer to show the energy savings. The architects have to specify the hoods. The researchers had to accept that motion sensors and automatic sash closing wouldn't be a problem for their research process. The environmental health and safety officer had to sign off on the slightly lower air change rates. The facilities personnel needed to say that they were prepared to accept additional maintenance, and the whole thing rolls through. You can see that that one decision about the fume hoods sounds very simple. Well, let's just use high-efficiency fume hoods with automatic sash closers. Actually took about 6 months of negotiation to get through the process. The overall result is that this building saves about 35% compared to a typical lab building on I-95, but actually saves about 24% when you measure it according to the LEED criteria, and that's because of the fiddles that happen in the LEED criteria baseline when you do the energy modelling. So I'm going to change tack a little bit. That was all about me and why I think I know something about energy. And I want to talk about why we think energy use in buildings specifically is important. I would say from 20 years of trying to think about energy in buildings, it's really, really difficult to get people to understand what it is that you're talking about. You can't see it, you can't hear it, you can't smell it, touch it, or taste it, and sometimes you're not even paying the bill. So there's very, very little feedback that tells you whether you're being an energy hog or whether you actually are completely an energy miser and use very, very little of it. And you can use calculators, and for those who are interested, those are great ways of doing things. But it really is quite difficult to understand what it is that actually you're doing. And I think that's one of the biggest problems about communicating this through design teams and through owners and actually through society as a whole. So why is energy use in buildings important? Looking at it, first of all, from the energy standpoint, this is a graph that shows where all of the energy is used in the US every year, and you can see that about 40% of the energy is used in buildings, and a good proportion more, some of the transportation energy use is used in getting to those buildings. You can also see that there's a roughly even split between residential and commercial building use, but you can also see that there's a huge difference between the way energy is used in each of the 2 building types. So these are averages over the whole US climate, so some buildings are hot and some buildings are cold. But I think you can see that for commercial space, lights and cooling tend to dominate the energy use. And in residential, it tends to be heating and the heating of hot water. And Procter & Gamble actually did a little sustainability study where they tried to work out which of their projects had the biggest environmental impact. And they came to the conclusion that the biggest environmental impact was actually in their washing powder. And the reason that it was in their washing powder was because everybody uses hot water to wash. So their story was that they would figure out how to do a cold water washing powder. And that meant that actually, although their process might use more energy, the overall energy use associated with the use of their product would go down. So you have to think a little bit about where you can make a difference and who and how can make that difference. The second thing I wanted to do was look at it from a carbon standpoint, and I know that you absolutely can't read this chart, but I am a carbon emissions and climate change believer. And I don't think I can really have any more conversations where I have to explain that the sky is falling in. So there needs to be another way of communicating about climate change. I also know that we're at a stage where we've passed the peak oil and that fossil fuels are finite. So there is an issue here around energy. But I think that it is important to recognize that there is a carbon connection with energy. So what the chart shows is on the left-hand side, you have energy. And all of the other things that contribute to carbon emissions. So it's energy, industrial processes, agriculture, and waste. And on the right-hand side, what you have is all of the proportions of carbon emissions and where they come from. And you can see that actually a very, very big proportion of the carbon emissions over the course of the year within the US comes from the energy. Just one other little detail, those 2 paler bars in the middle are actually the energy use associated with residential buildings and commercial buildings. So you can see, similar to this previous slide, that there's a pretty big proportion of carbon emissions that is due to energy use, specifically in buildings. Oh, that would be the wrong way. Just as an aside, and because I live there, in densely populated areas like New York, transportation energy use is a much smaller contributor to carbon emissions than in the region as a whole, because the city is so small and so many people don't drive. So if you draw a boundary just around the 5 boroughs, you can see that the carbon emissions associated with the transportation are actually those 2 blue ones, the 17% and the 3%, so it's about 20%. And all of the rest of the carbon emissions associated in New York are associated with energy use, either in buildings or in streetlights. The point that I wanted to make here was about boundary issues. So it's very easy for New York City to draw a boundary around the 5 boroughs and say, hey, look, all of our energy use is in buildings, and actually all of our carbon emissions are associated with buildings too because of the way that that works. But they have sort of forgotten to point out that New York City, without a lot of trucks coming in, bringing stuff like food and materials for doing work, would actually not survive all that long. So this question of where you draw the boundaries and how you draw the boundaries around energy and emissions is actually a pretty key concept both in sustainability and energy. It's understanding what you are really accountable for. So why are engineers frustrated about energy in buildings? Because for the most part they are. The first thing is that nobody knows what we're talking about. Energy is power times time. Energy is measured in joules, BTUs, kilowatt hours. Power is measured in watts and BTUs per hour. So power is the rate at which energy is used, is the other way of saying this. Why should I care that I have to tell you this? So this is a little bit complicated, and I know it's numbers, and I know some of you are architects, but here goes. If we cut the peak solar load in a perimeter zone by 50%, which I think we would all agree is a huge cut and really worthwhile doing, and then we work that through and we figure out what that means in terms of energy, the solar load is probably only 25% of the load in the perimeter zone. And in a big American building, the perimeter zone is probably only 25% of the overall floor area. And actually, the sun doesn't shine on a hot day for more than about 20% of the occupied hours of the building. So the annual energy savings for the building for this savings is 0.5 times 0.25 times 0.25 times 0.2 times 100%, which is a little bit less than 1. So we shouldn't dismiss a percentage energy saving of less than 1%. We started off this conversation with an idea that 50% of the load is reduced, 50% of the solar load is reduced. That is a power number. And over the course of a year, that comes down to a 1% energy number. But my experience of modeling shows pretty conclusively that a 50% energy saving is actually made up of about 20 good ideas and correct decisions. So a 1% energy saving is actually pretty important. You need a lot of 1s and 2% all the way through your building design process in order to actually hit 50%. There isn't any one thing that you can do that nails your 50% right there. We should also absolutely not dismiss capacity changes and solar load reductions. One of the issues that I have been coming across more and more recently, especially as energy modelling gets easier and everybody learns how to do it, is that everybody always asks me, how much energy does it save? But that's actually often the wrong question, because the other relevant elements in the design of HVAC systems in particular are comfort, are glare, peak capacity, system size, space take, and all of those are influenced by a change in peak load. But almost all of them cannot be measured in terms of an energy saving or in terms of a definite payback period. So sometimes asking the question about energy is the wrong question, but it is the question that we always ask. And this not being able to separate energy from power and understand whether it's a 50% cut in something that happens for an hour or whether it's something that makes a difference every hour over the whole of the use of the building is a huge kind of mental leap. So nobody knows what we're talking about. They don't know the difference between power and energy. The second thing nobody knows what they're talking about is they don't know how to define zero energy. When I say they, I mean we. But what I'm trying to get at is, this is the federal executive order, which this may not be obvious to you immediately, but it is a complete dog's dinner of a description. Zero net energy means a building that is designed, constructed, operated to require a greatly reduced quantity of energy to operate, meet the balance of energy needs from sources of energy that do not produce greenhouse gases, and therefore result in no net emission of greenhouse gases, and be economically viable, just by the way. So what they're saying here is that they're not really interested in zero net energy. What they're actually interested in is zero net carbon. And those two things are actually quite different. And the fact that this definition is so screwed up, and that it's the one that's put forward by the federal government, means that actually the whole industry is a bit confused about this. What is it we're trying to do? Are we trying to reduce the energy, or are we trying to reduce the carbon? So my first project, that cafe, had solar panels on the roof. We didn't change the amount of energy that the dishwashers needed to make hot water in order to wash the dishes. What we changed was how much that energy was going to cost, because we got it from the sun, and what the carbon emissions associated with it were. And if you think about things that way, you realize that you actually get driven to completely different decisions depending on what it is that you're trying to reduce. So I had hoped that this graph would be much more conclusive than it is, but it isn't, and that's largely because I've got transport in there which outweighs everything else. But what I'd like to show you is that the carbon emissions associated with lighting are not the same as the energy emissions, and that actually when you convert from carbon to energy for lighting, it goes up, but when you can't convert from carbon to energy for heating, it goes down. And there are all sorts of little anomalies like this, where the electrical energy tends to be one thing, and the energy that's provided by burning fuel tends to be something different. The other thing that makes a difference is whether you measure it by sight, as in what comes through the meter for the electricity and what comes through the pipe for the gas, or whether you measure it in terms of the source energy, as in how much power gets provided to the power station in order to provide that amount of energy at the building, compared to the amount of gas that you put into the building as a source. So there's a boundary issue, which is what I was trying to say about New York City. Measuring the boundaries and understanding where they are is a huge, it's a hugely complicated thing, but you have to sort out what those boundaries actually are. So the third frustration for engineers when they're talking about energy is that everybody is an expert, because I can guarantee that every single one of you will have read some article somewhere that says, if we just put ground source heat pumps in, we would save X amount of energy. And that's not necessarily wrong, because ground source heat pumps can actually be a really good solution. But sometimes they're not a good solution, and I have probably on about 4 or 5 projects I have had to do an analysis to show that ground source heat pumps really don't work, when actually it was obvious by inspection in the first place, but my saying so wasn't enough. We've produced the thing, we've rolled through the numbers. We could have actually spent that time doing something more useful, like designing a more energy efficient system rather than trying to put in a technology that didn't necessarily fit. The other thing I would say here is that all of these solutions can be great, but every single one of them will only give you 1 or 2 or 3% on your energy use reduction numbers for the building. So you actually have, just because you've done this doesn't mean you've actually solved the problem. You have to go ahead and do a series of other things. So, what are the things that I think that you should know? There are 3 things I'd like you to take away from this. Don't design an all-glass building. It takes a little bit of everything to save the most energy, and the more energy that you save in operations, the more significant embodied energy becomes. And in this particular case, you can substitute carbon for energy because it's the same equation. So why shouldn't you design all glass buildings? Actually, the first reason is that the energy code says you're not allowed to. But there are a lot of them around. And if I had $1 for every time that somebody said, why can't I do an all glass building? There's one down the road and it works perfectly well, I would be rich, really rich. So why does the energy code say what it does? We did a little bit of an analysis, a kind of outline, back of the envelope energy code analysis to understand why it is that the code says this and why it is that it is a sensible idea. So we did 4 different glazing types, 4 different percentages of glass for 3 different climates and 4 different building shapes. What you're seeing here is the first 2 of those options. The 4 glazing types we looked at were single glazing, double glazing with a low E coat, and triple glazing with a low E coat. And the 4 glazing percentages we looked at were 20, 40, 60, and 80. That's what the diagrams show. We looked at a variety of shapes of buildings, but I'm going to present the results for the square one with the core in the middle, because that's the one that makes most sense. So what can you see from the chart? Type 1 is the single glazing, and that's the one on top. And type 4 is the triple glazing, and that's the one on the bottom. So what you can see, and the axis along the bottom is the glazing facade percentage, and the axis up the side is the energy consumption. So what you can see is that the better the glass, the type 4 glass is the best glass, the less the effective glazing percentage, the difference between the height of the ends of those 2 lines. But it's still actually quite significant, and nobody puts in triple glazing. Most people actually opt for the blue line, the type 2. So in the northeast, type 1 glass is actually essentially illegal, but I think you can see why from this particular presentation. You can see that actually it varies so much. The energy use varies so much if you use a type 1 glass that it becomes very, very difficult to figure it out. So the second thing, this is the data for all of the analysis plotted together, so it's a pretty dense chart. But you'll notice that the charts are plotted in terms of cooling capacity and heating capacity, i.e. it's about peak power. It's not specifically about energy use, because actually the peak power, the peak capacity is actually the bigger part of this story. The way the chart's organised, the back row, I guess that's a purple line, is 80% glazed. The front row, that's the blue line, is 20% glazed. The glazing types are organised along, so type 1 is on the left and type 4 is on the right, so the glass improves as you move from left to right. As you can see, maybe, New York is the most extreme of the climates. It gives the biggest load for heating and nearly as big a load as for cooling as Miami does. The interpretation of these charts in terms of energy is tricky. Miami hardly ever goes into heating, while New York stays there for a lot of the year. So the Miami energy figures are completely dominated by the cooling plant, and the New York energy figures are completely dominated by the heating plant. So why not design all glass buildings? This is about the prioritizing the priorities. We designed a residential building, where the architect said that the best thing about his building was that it had floor-to-ceiling glass, and that gave her an absolutely bitching view. That's what it said in the newspaper. But if you have an energy goal, and by law you do, you also have to check which is the priority. Do I want floor-to-ceiling glass, or do I want an energy analysis that is done correctly? And you don't have to not have floor-to-ceiling glass everywhere. You just have to limit where you put it, which means you have to actually think about why you want it and where you want it. You have to prioritize the priorities in order to make sure that you get that right. So the first thing I'd like you to take away is don't design all glass buildings. They waste a lot of energy, and they waste a lot of installed cooling and heating plant. The second thing is that it takes a little bit of everything. So I'm going to show you 3 of these, but this is the model from a fictional building that we made up for a zero energy study. It has residential, commercial, and parking within it. It's about 1 million square feet. And we looked at 13 different energy saving measures and combinations, including improved facade, daylight, low energy lighting, underfloor air versus VAV versus chilled beams, heat recovery, high efficiency motors, high efficiency chillers, high efficiency boilers, regenerative elevators, PV, and minimizing the runtime. And you can see that for every one of those changes, we got a little bit. And we did 13 analyses, and we put together the ones of those that make sense to use together, and that got us to about 55% of the energy use of the code-related building. So it's clear that there's really no magic bullet. You have to do a bit of everything. Once we'd done all of this, which is all about reducing the site energy, the energy that actually gets piped to the site, we then added a CHP to it to see what difference that made. And what that did, of course, was it pushed the site energy way up, because we suddenly are operating a power plant on the building. But then we analysed it in terms of source energy, so the electricity that would have been coming from the power plant. Actually, our CHP, where we reused some of the heating, was a much more efficient way of getting heat to the building than using a gas-fired boiler. So when you started measuring it in terms of source energy, the CHP actually made a big difference to the energy use. We actually got this thing down to about 50% of 2001 energy code. to show that it wasn't a fluke for Houston, here are some figures for London. This design exactly won't be built, but these are the steps that we went through, and this is a little more user-friendly because the charts are actually labelled. The first column is basically the standard design, what we thought that we would do. A very energy-efficient standard design, but standard nonetheless. And then we dropped the lighting energy load to about 2/3 of what it says in code, and you can see that we actually made a pretty big difference to the energy code indicator. We then changed the filters. Instead of having one big bank of filters, we doubled the area, which reduces the pressure drop, and that gave us another pretty big chunk of saving on the air side for the energy. And the nice things about lighting and filters are that they affect the systems for every hour that the building is actually operating. And this building operates 24 hours a day, 7 days a week, so we got good savings from those things with small increments, but lots and lots of time. We then looked at what happened to our carbon. EPC is measured in terms of carbon rather than in terms of energy. If we put in a biomass CHP, you can see that we again got a very big drop, and we got rid of that heating energy load because we absorbed it into our CHP. We then looked at what happened if we added photovoltaics, and you can see that we had a tiny little additional drop. And then we looked at what happened if we put PV on absolutely every square inch of the site that we could manage, so we multiplied it by 10. And you can see that we actually started to make a pretty big inroad into the overall carbon emissions of the building. So there are a lot of things in here, but again, the changes look more dramatic than they did for the other one. That's partly because it's measured in terms of carbon rather than in terms of energy, and because we put this biomass in there. But you can see that, you know, in order to get down here, we had to do some things that are pretty extreme. They're a little bit beyond what current practice actually is for buildings. And then I said I was going to show you three. Here's number 3. These are some figures that we generated for a current exhibition that the AIA are putting on in New York. And we wanted to know what the effect on the overall energy use was of decisions made at different stages during the design process. So the first one was a fictional building, and we just tried everything. The second one was a real building that had a 0 carbon goal. We just wanted to, so we were aiming for carbon rather than energy. And then this one is about where are the decisions made in the process that actually allow you to make the changes. I don't know if you can really see. The first decision was about site, and the bottom orange bar is about transportation. And what we did here was we compared what happened if we put the building that we were looking to design in a greenfield site compared to putting it on the corner of 30th Street and 9th Avenue in Manhattan. What happens when you move it from one to the other is that you change the transportation mode from being all single-person car to being primarily public transit oriented. And if you look at the figures for public transit versus personal car, what you find is that the energy use associated with the energy use and the carbon emissions, specifically the carbon emissions associated with the location of the building, are actually, it's the biggest step that you can make is to build in urban areas with public transport systems. We then looked at what happens when you pick the site, and we were really then looking at what shape should this building be? Should it be a rectangle? Should it be a square? Should it have a core in the middle? Should it have the cores at the end? Should it be oriented north-south? Should it be oriented east-west? And the best saving that we got from this was actually with a building bar that's oriented along an east-west axis, so the big facades are north and south, and with cores at both the east end and the west end. We then looked at what happened with passive design. So we wanted to see whether we could save money with shading, with the distribution of windows, and there's another piece of carbon that we saved there on the third column. We then looked at active systems, specifically how much can we improve the air conditioning systems, how much can we improve the chiller, how much can we improve the pumps and motors. That gives us the next chunk. We then looked at materials, just to see whether there was anything there. We looked at the construction process, and then we looked at operations. And this chart actually also includes an embodied energy component. So this was the slide that I put in so you could see what we were thinking about at every stage of the project. And then this is the slide that shows where the embodied energy is. So if you look at the beginning, this blue bar on the first thing, it's actually pretty insignificant. But by the time you've driven down all of the energy uses for operations, the carbon emissions, the energy, the embodied energy and the embodied carbon associated with the building actually begins to become quite a significant component of the building itself. So the metric that we developed was something that we called the annual energy, the total annual carbon footprint, which was deemed to include the transportation for people getting there, the building operations itself, and an amortized amount, which was to do with the amount of embodied energy in the building. So how do you get the embodied energy or the embodied carbon of a building down? This is a piece of work that we did, again, a little bit theoretical. The red line at the bottom shows you the embodied energy. And you can see that every 10 years we made an assumption that you had to do something to the building, buy a new chiller, paint the walls, move the partitions around, something that increases the embodied energy pretty significantly. And then the purple line is the operational energy. And what you can see is that right at the beginning of the use of a building, the operational energy is way, way less than the embodied energy. But there's a crossover point that happens after about 2 or 3 years of building use, where the operational energy and the building embodied energy come to be about the same. And you can see that the longer you extend the life of the building, the more significant the operational energy becomes. So, one of the most powerful things that you can do with buildings to decrease their total annual energy footprint or their total annual carbon footprint is to make them last longer. So that's what this slide says. Please make your buildings last longer. And then finally, because nobody ever really shows these figures and because they're fun, we looked at how much embodied energy you actually put into individual materials. And the metric that we used, we decided that barrels of oil would be the right kind of thing to use. It's visualizable and makes a difference. So here is a set of barrels of oil sitting somewhere scenic, probably Alaska, given the icebergs in the background. And with every one of those barrels of oil, you can make some materials. So you can make 240 kilograms of steel. You can make 1.5 tons of sheetrock. You can make 400 kilos of hardwood, which of course is all about transportation. You can burn 265 kilos of carbon, 265 kilos of coal. So you can begin to see from this the relative energy density of coal and oil and why oil is so much preferred. You could make 200,000 cups of coffee. We just did the boiling of the water. We didn't do the harvesting and transport of the coffee. It was just the boiling of the water. You can treat 800,000 gallons of wastewater. You can feed 430 people for a month. What we did there was just calculated the calories that 430 people would take in over a month and equated that to the energy in a barrel of oil. We didn't look at the food miles or the embodied energy in that food. We just looked to see. It was for fun. And then we also figured that you could burn this many kilos of coal, or you can burn this many kilos of wood pellets. So this is really just to give you an idea of the different magnitudes of things that you get when you start looking at how much embodied energy you get in a particular thing. So that's my whole presentation, and I think it's question time. It would be good if I could see you. Probably good if you could see me too.
Fiona, can you talk a little bit about how you, what your process was with the project in Caledonia, and how you actually went through and developed systems that would, and what were the systems that were developed to cool these buildings?
So the answer to that question is that the system that we put in was actually a fan coil unit. Very exciting stuff. The things that we did with the buildings, those cars, the things that do this, they have a building associated with them that comes to sort of half height. That I think you could tell from the slide that the cars are very, very tall. And there are openable windows at this end of the building, and there are also openable windows here. So we created a path for cross ventilation. And then we located all of these curved shapes so that the prevailing wind blows this way. And what that does is that the prevailing wind creates a suction on this side of the project, on this side of the fins, basically, that pulls air through. So you could either operate it with the fan coil system, which is a relatively simple system to maintain and operate, or you just let the wind blow and open the doors at the back, and then that sucks all of the air out so that they had continuous ventilation. That landed the right way up.
And did it also work with like the heat stack effect, where the heat was hot, you know, the hotter
Yes.
air is higher, so it created the curve, created a chimney. Is that right?
The fact that the curve, the fact that the cars, the fin is so much taller than the rest of the building did create a stack effect, but actually it's pretty hot and sticky in Caledonia. It's almost as hot and sticky as it is in here this afternoon. So the buoyancy-driven effect, we didn't really want to wait for that, because you get a bigger effect the bigger the temperature difference. We would much rather wait for the wind to blow and have higher air change rates.
When you did biomass calculations, did you calculate, where did you draw the box?
When we did the biomass calculations, we sort of cheated for the one that I showed you, because we used the standard. We did it in the UK, and the UK have rules about what the carbon emissions factor is. So we used their standardized carbon emissions factor. If I was doing it for a project that I didn't know about, I would look at where it was grown, where it was delivered, how it was stored. So I would use the whole of the supply chain calculation. Yes. Let's see if I can find it. This one that you didn't get to see because it was hidden, but that I meant to show. This isn't the one that you were looking for, is it? This is the one that I was looking for. This is the graphical data from the table on the slide before that shows how those comparisons work. And what I was hoping was that I was going to see something a little bit more different between them, but I didn't, and that's partly because I think that what we did here when we calculated the numbers, we used source energy and source energy and carbon tend to be somewhat similar. Whereas what happens if you compare site energy and carbon is you get a big multiplier on the electrical results. So that's why I think this isn't as conclusive as I had hoped that it would be, and it's my fault for getting somebody else to put the numbers together for me.
What comes to mind for the best performing building you've ever taken part in design and construction, and in terms of actual performance, measured performance, and how did it get there? So
one of the problems with my job is that we never actually go back and measure what we did. We do everything on the basis of what we think it's going to be, and I don't think that's necessarily a bad thing. If we didn't do the calculations to see which would be more energy efficient, you wouldn't end up with more energy efficient systems. But what happens is that it's unusual for us to go back and measure. The clients don't want to pay, and we certainly can't finance it. So one answer to your question would be that actually Stanford did call us back. We did an energy model for them that showed that they would use X amount of energy, and when they opened the building, they found that they used 2X. So they said, what's going on here? And called us back and said, well, figure it out. So we built a further calibrated energy model, which we calibrated to the current building energy use. And then we did a baseline energy model that took the calibrated model and then looked at what the baseline would have been. And what we discovered was that they were operating the building for twice as many hours as we had predicted in the energy model. And the biggest single determinant in how much energy used is how many hours you operate the systems for. So when we did the calibrated energy model, what we actually found was that the energy saving was twice what we had predicted, because the baseline energy use was so much higher. So I think that's actually a very interesting lessons learned story for us, is that we actually got to go back and understand what we did, and our conclusion was that our energy model actually wasn't bad. It's just that we had not the right data when we put it in the first place. And there is a general misunderstanding about how accurate those energy models can be. We say things like, well, they're plus or minus 10%, and that's right, but that's only right if you get the assumptions incorrectly. And that's, it's often just not properly known.
Yeah. Do you think that codes will ever deal with actual performance rather than just design? In Europe, as opposed to here, perhaps, maybe?
Oh, in Europe, they actually already deal with it. They have the European Building Performance Directive is a piece of legislation passed by the European Union about 8 or 10 years ago, which every country has adopted in a slightly different way. But the two components of it are that your building has to have what's called an asset rating, which is really a measure of how efficient the systems are compared to a baseline system. And that's measured with a fixed occupancy, fixed schedule, fixed everything. And the baseline building is pretty much fixed too. And that's what they call your asset rating. And that's what the EPC numbers are related to, which is actually what that chart that I showed for London was measuring, was the EPC figures. They then have a second thing that they require you to do, which is called a display energy certificate, which is that you have to put your actual energy use benchmark up in the lobby of your building. So if you're a publicly accessed building, you have to have a certificate up in your lobby that shows, sorry, let me just see if I can find the picture. That thing up there in the top right is an energy performance certificate, display energy certificate. And that's what you get up in your building as a little chart that says you're green if you're at the top and red if you're at the bottom. And that's a benchmarked energy use for your actual building. And they require that it's right there, and you definitely have to produce it if you sell a building, even a residential building. In New York City, there is now legislation that every building over 50,000 square feet has to put its energy and water use into a database. It actually uses Portfolio Manager from Energy Star, and that is not public this year, which was kind of the code official described it as a mulligan. We'll give 2011 a mulligan, and 2012 you have to put your energy and water data in, and it will then be published 6 months after the due date. So there's beginning to be more of a move towards publishing some of this data, but it's very piecemeal, very much on a city-by-city basis. Can't remember what else I was going to say. There was something.
Sounds awfully radical for the United States.
Yeah, I think it's a little difficult. The answer to the other question that you asked, which was what's the best performing building I've ever worked on, is probably Yale School of Forestry, where we have some measured energy data for that, and we think that we use about 25% of the energy that the code says that we're allowed to use through building design and efficient systems and ground source heat pumps with standing column wells and some solar thermal and some solar PV.
KBTU?
Don't know off the top of my head.
Was there a specific reason you decided to join this industry?
That's a good question. I think that I had very bad career advice when I was in high school, and I thought about being a doctor, and I thought about being a lawyer, and I realized I couldn't stand the sight of blood, and I didn't think I was argumentative enough to be a lawyer, and the only other thing I could think of was an engineer. Now that I'm a bit older and I've seen more people, I might have made a different choice, but actually it's proved to be very good for me. It's a problem-solving career, and I have enjoyed my 20 years in it immensely. So I think I made a good decision for the wrong reasons.
What about like the building energy tool?
Well, that I also fell into. I have a degree in structural engineering, and I went to work for Arup, and they thought that I was a mechanical engineer, so they put me in the mechanical engineers R&D department. And by the time I came out of that, that's what I knew how to do. So, so I spent probably the first 3 or 4 years of my career being completely undertrained for the job that I was trying to do, but also very expert in some of the detailed analysis work, because that's what I had spent the first year out of college doing. So I tried to switch to structural engineering a couple of times, and it just didn't happen. So I'm still here, still doing energy-saving work.
Could you talk a little bit about just integrative design in terms of when the engineer should be best involved?
I think that the big issue with integrated design is understanding what the goals that you're actually trying to meet as a design team are. And I don't think it really matters who sets those goals, as long as they're clear and the trade-offs between them are set. So as an engineer, of course, I would say that day one is the time to involve me. I can come and give you strategic advice about energy right from the very, very beginning. But actually, if you don't involve me on day one, you don't get me there till day 3. As long as your goals are clear, and as long as you actually have articulated that you want an energy goal that is possible to achieve, that works too. So I think the beginning is good, because then you can actually put the ideas in from the beginning and sometimes shape the way that the building is put together. I mean, you can see from the chart with the transportation energy that the site and the buildings and the program actually do have energy impact. And you aren't going to understand those as an architect or as an owner if you don't have somebody at the beginning who can actually do the analysis for your particular site and climate and idea. But it costs money, and people don't always want to spend it, and not all of the problems are uncorrectable later.
And so when you are approached by someone along a more traditional course where there's a lot of architectural work, design work that's already been done, and you feel that it's really compromising a lot of the opportunities for energy savings, how do you share this information?
Well, that's when how you communicate all of this actually becomes most difficult. I would say that I have been lucky for my whole career that I have always been involved at the beginning of schematic design. I've never had to wait until the end of DD or even the beginning of DD. And I think that if I had, I might have a different view about what's correctable and at what stage.
Given the importance of heating and lighting in the overall energy picture, particularly in residential buildings, the skin of the building is clearly significant in all of this. Your rule about not all glass, has some significance, but all of the kind of extraordinary insulation that is now becoming part of the LEED's view of the world, you haven't really emphasized that here.
One of the reasons is that most of my professional work has been in commercial buildings, and very little of it has been in residential buildings. If you look at projects like the Beddington Zero Energy Development, which is a project from the mid-90s that Chris Twin, one of my colleagues, led, they did a great deal of analysis about building envelope and how much effect that has. And the Beddington Zero Energy Development, BedZ, has 12 inches of insulation between 2 leaves of brick. All of the big windows face south. There are no windows pretty much except for some daylight facing north. The whole thing is arranged as a terrace, so there pretty much are no east and west facades except at the very, very end, and those are pretty much blind walls. That building also, it works a little bit like a passive house. It's very much sealed. It has a mechanical ventilation system. The mechanical ventilation system with heat recovery is driven by wind that sits on the roof. There's a whole series of things that happens there. So I think in residential, where heating is actually a much bigger consideration, certainly through the whole of the northeast, and also through the whole of Northern Europe, that insulation is actually worth quite a lot. It's worth an enormous amount of energy when you're building new. It does cost more, but actually in some cases, the whole passive house thing is built on the idea that you can practically run without systems if you get your energy right, if you get your insulation right. And I think that's true, and I think if you've got the kind of building that works for, that's absolutely the first line of defense. In London, they tell you what they think the rainfall is going to be in 30 years' time and expect that you'll design for it, and they have standards that tell you what they think the design temperatures are going to change to and how much windier it's going to be and so on and so forth. And the UK is a small, very densely occupied country. There is not equivalent data for the US, so anything that you do with the potential for climate change is essentially a guess. So we try very hard to right-size our systems. It makes the controls work better and it keeps the energy use down. So we tend to not put too much fat in there for, in 2050 it'll be 5 degrees Fahrenheit warmer than it is now. But it's a completely valid concern. It's just we don't have any good information, so we assume we have no information at all, which may not be the right approach.
back to the pie chart about the total energy usage of the different industries, or or the energy usage from industry, from buildings, and from transportation. Can you foresee a sizable decrease in the building chunk, or perhaps maybe if we were looking at CO2 emissions rather than energy?
Yeah, this. If you look at CO2 emissions and you look at source energy, they are actually more or less similar. So you only get a mess with the difference between energy and carbon if you do it at the building level. So I don't know whether I see a change in the proportions, because I think that the transportation people are actually also working very hard to get their carbon emissions down, and the building people are trying to work pretty hard, and the industry people always work hard because it goes absolutely to their bottom line. So this ratio may not change very much, but the size of the pie might.
At least not grow.
Sorry?
At least not grow faster.
At least it might not grow faster. I mean, it tends to grow when the economy is growing, and it tends to shrink when the economy is shrinking. I have a chart that shows energy use compared to economy size, and the lines just track.
You said this is for New York City, right? Pie chart?
No, this one's actually for the US as a whole.
Oh. So
New York City shows 80% of the carbon emissions or source energy use is in buildings. 80% in buildings. I can't remember where I started that sentence.
This is a weighted figure for the country as a whole?
It's done on source energy terms, so you could turn this into barrels of oil. It's about the energy input that goes to the various sources. So it's not really weighted. It's just the sum.
You mentioned LEED a little bit. I was just wondering when that criteria started appearing more.
Okay, so the LEED pilot was 1999. So that was the first year that any buildings even tried. The first building that we looked at was the Oka Park speed skating oval in Salt Lake City for the Olympics, which actually was one of the first buildings that got LEED Silver in the pilot program. I think that, I think LEED 1.0 might have been 2001, something like that. And then it went from there, and we're now in LEED version 3.
You mentioned that the U.S. government confuses net zero carbon with net zero energy.
Yeah.
What sort of problems does that cause for your industry?
So the real problem that it causes is if you really were aiming for net zero energy, then you would actually attack the hours of operation and the energy efficiency of all the stuff in the buildings, the computers, the lights, whatever. If you don't really care how much energy you're using, but you care about the carbon emissions, what you'll actually look at is a substitution of the grid. So you will try to make the grid less carbon intense, or you will try to produce electricity that doesn't need carbon on your building site. And they're two quite different things that affect two quite different industries. That's the first sort of level of confusion. At a very macro level, you do two completely different things depending on what you think the goal actually is. The more immediate problem at the building level is that people tend to look at site energy, and the electricity carries a carbon load of about 3 times what natural gas carries for site energy use. So if you're only thinking about energy, you'll drive your electricity use down, and you'll drive your gas use down by the same amount, because you're only looking at the site energy. As soon as you start looking at carbon, you actually start focusing much harder on the electrical energy use and much less hard on the heating generating pieces. So it's not so much a problem, because actually what you want to do is, in both cases, is reduce the amount of energy you require, change the efficiency of the equipment, and then, for the case of the carbon emissions, substitute the source for something that's less carbon loaded. So that the first 2 steps are the same, but the third step is different.
Have you looked at passive survivability as one of the criteria in designing buildings, so that buildings can actually survive, other than in Caledonia, for some period of time without the systems running at all?
It's generally not a strong criterion unless you've got some reason to make it not. to make it so. So in Caledonia, it was absolutely primary. In most other buildings, we look at the level of redundancy and resilience if it's important. Most office buildings, it really doesn't matter if they shut down, if there's a hurricane or a power cut or a flood, that you just deal with it afterwards. The types of buildings where we do worry about it are museums, galleries, data centers, the kinds of things that you want to keep running or at least shut down slowly if there's a disaster and then you want to bring them back online quickly afterwards. So those kinds of buildings, we begin to look at the resilience, and passive survivability is always a component of that. Although, you know, the brute force method is preferred by most clients.
Going back to the net zero building, the last sentence, making it economically viable.
Yes.
On the slide where you showed the different modifications from the baseline, do you have any information regarding which ones are cost effective? Because it just kind of showed the
So this
the
one?
drop. Yep. Do you have anything that ties into cost?
On this one, we did everything that we thought that we could do with current technology, which is why we got stuck at 60%. So we did lighting, and when I did this was 2006, LEDs weren't really a possibility, so I had T8s in there, T5s in there as an option. And everything else was stuff that we thought could pay back. It wouldn't necessarily pay back, but we didn't look at the other side of the equation. That's the fun thing about a fictional building. For this one, we did have to look at payback. You know, CHP doesn't pay back. There's no question about it, which is the other thing. If you're interested in reducing energy, then you would never do a CHP. If you're interested in payback, you'd never do CHP. But if you want to get to carbon neutral, then suddenly CHP is a huge component of how you probably will get there.
Well, it depends on where you are and what you monetize.
It does completely depend on where you are and what you monetize, but it also, in carbon terms, the CHP can help you get there. In energy terms, sometimes it does and sometimes it doesn't. And you know, the lead models aren't much better because they actually measure energy in terms of cost, which is also a pretty poor metric.
I'm sorry, I'm an architecture person, so I've got kind of a dumb question, right? So can you explain what a biomass CHP is for us ignoramuses?
So a biomass CHP is a combined heat and power plant. So it produces heat and electricity, and it produces it using wood pellets. That's the biomass bit. There are other forms of biomass, but that was what we used in this particular case.
Okay.
On the previous slide, each interval seems to decrease in energy for except for case 6 with E down there. I don't know if you remember specifics of this.
I don't remember what I put in each one of these. The reason why it gets less as you go on is the law of diminishing returns. The better you are, the harder it is to improve. What happens in case 6, I think, is where we changed the facade so that we basically managed to cut out the heating load by improving the facades in the residential component of this building, which was about 400,000 square feet.
As an engineer, what do you think the biggest disconnect is between the architecture and engineers and how they, I guess, go to energy, and you know, positive or negative?
I think that the biggest disconnect is that for an engineer, energy is about a mathematical calculation. And for an architect, it's not about a mathematical calculation, because most architects I know, even the very good ones, are not especially comfortable moving through numbers. They can do it if they want to, but the ones who are very good at design and have the best ideas aren't always the ones who have the best handle on how to do the math. And energy saving over the course of the year is, for an engineer, as I said, a mathematical problem. So I think we just communicate badly about it. It's like, well, we show you the numbers and you say, well, what is it you don't understand about this? And you say, well, what is it you don't understand about my great idea for a ground source heat pump or a photovoltaic array? Or don't you think that this window looks better this size and this shape? And it's two completely different conversations.
In your first slide, immediately I think you mentioned a really extraordinary payback period of 20 years.
Yep.
In your 20 years, have you noticed any changes in attitude for payback periods? Not so much in Europe,
20 years is extraordinary because it's long, for those people who hadn't picked that up. A typical developer will look for a payback of about 3, and a university will look for a payback of about 5 to 7. And any 7, there we go. And any longer is sort of unspeakable. There are reasons for that. One is owner-operators hold their buildings for longer, which is where the universities fall into. So they actually, the people who build the building and pay the money realize some of the benefits, so they actually think they might be around long enough for the payback to actually affect them. The problem with developers and people who buy to flip or buy to rent or whatever it is, they don't always see the money come back to them. So if the payback is not actually really short and it doesn't give them some marketing advantage, they're not necessarily happy to do it. And no, they have been about the same for the last 20 years. Anybody got anything else? Because I know I'm done.
For coming. We'll see you in 3 weeks, and please hand out your feedback forms to the students in the back. Thank you.